So today we finally are going to get into the quantum part of the course. Last week we started by introducing essentially classical field theory description of a problem, and we saw two examples of how to derive a field theoretical description for a problem where the number of degrees of freedom is very large and in fact infinite. And we saw two examples of that. The first one was elastic string in 1D, and we showed that just starting from the classical mechanics, we can write down a Lagrangian density in terms of a local displacement field, its space derivative, and its time derivative. And this is how it looks like. It's half m time derivative square kinetic energy minus the potential energy, which is expressed in terms of the space gradient of the local field phi, and phi physically represents a displacement of the atoms or the particles coupled on the chain from their equilibrium position. So that was a problem where we started from just knowing how to write the Hamiltonian for a classical system on a discrete chain, and we went to the continuum limit. That was one example. The second example, we derived field theory basically by making an educated guess. We started from the equations of motion that are supposed to be Euler-Lagrange equation of the action or the Lagrangian, and we deduced a Lagrangian by looking at what are the fields that should appear in the theory and making a guess that is consistent with the symmetry and is the simplest one to write. Okay, that was our strategy for the second, and that's the electromagnetic and the Lagrangian density. And again, I remind you, the Lagrangian density has units of energy per unit volume, and it's something you have to integrate over the volume to get the full Lagrangian, and you have to integrate over time to get the action. Lagrangian density for the electromagnetic field is expressed in terms of the field A mu. So mu here is there are the four vector components of the vector potential, and its derivatives, which are encoded by this tensor called f mu nu. There is something I want to, let me first finish writing the Lagrangian. So the form that we got, and today actually in the tutorial you're going to see how we get the coefficients, but it's basically this form. Okay, that the first term is just electromagnetism with a product that is actually an invariant scalar. And this is the coefficient that we called C1 last week, but Sarah will show you how to get the number. And plus, there is another term that describes coupling to the matter field, the current and the charge density. And this is it. This is the electromagnetic action where there is one thing that I wanted to comment on, and I forgot last week, which is when I'm defining F mu nu in this relativistic form, it is basically d mu a mu minus d mu a mu, and notice that the mu is t x y z. Now you can see from the expression that both all components of A and all components of the derivative have the same physical units. But it's we have to be careful about it because space and time don't have the same units, right? There is a constant that relates them to one another. What is this constant?
C.
C, exactly, it's the velocity of light. So by using this definition, both for A and for the derivatives, I'm assuming units where C equals 1. This is usually what you do in physics in general. Sometimes you can choose your units. I mean, you can choose CGS, MKS, all these complicated things, but for the purpose of getting the physics right, sometimes you can have the freedom of choosing your units. And in this case, and for relativistic problems that are Lorentz invariant, it is very convenient to work in units where C equals 1. Okay, so we have to stress it because it's going to come back to us when we try to restore units. Okay? So, okay. So both of these expressions are examples of field theories that in principle you can think of them as classical theories. If the local fields, phi or A, are just numbers that get a well-defined value for each point in space and time, then this is a classical theory, okay? When do they become quantum? If the fields are no longer numbers or something that gets a well-defined value at any point and any time, but rather are replaced by operators, and operators can obey some non-trivial commutators, and that's what we are going to do today. We're going to quantize these theories, okay? And then you'll see that by doing so, we are going to basically get emergent degrees of freedom that are in fact the true degrees of freedom of the problem. And they are not going to be the original particles coupled by springs that we had in the mechanical example. And in the second example, we don't even have degrees of freedom, right? We started from some field, from Maxwell's equations and so on. So, but we're going to see that for both problems, we can define particles, or rather, let me call them quasi-particles, that are serving as the degree of equilibrium, and they are quantum particles. Okay? Okay, so how do we do it? So the first example, we'll do it first for the first example, because this one is the easiest to quantize. Why is it easiest? Because we can go back to the original Hamiltonian. Remember how we started? We wrote a Hamiltonian for the chain, right? And in this Hamiltonian, we had coordinates and momenta of particles. Now, if these particles are quantum, we already know how to quantize. Okay? We don't even have to think, because the momenta and coordinate obey canonical commutation relation. Okay? So we are on very safe ground. We can start from this and then go to the continuum limit, and you'll see. Okay, so this is what I'm doing now. Quantization of the 1D string problem. Okay, that's the title of today's talk. See everything? Yeah, very good. Okay, so so let me write the Hamiltonian. And now I'm writing it exactly as I did in the first stage of all this derivation. I go back to the chain, so I just remind you that the problem was that we had these masses connected by springs. This is K. Okay, and then we went to the limit where the lattice spacing is very small, and we went to the continuum limit. But this is what we started for, and the index n plus 1, n plus 2. Okay, these were just indices describing discrete particles with mass m. The kinetic energy is Pn squared over 2m, and the potential energy is half k sum over n of Rn minus Rn plus 1 minus A squared. Okay, that was the original Hamiltonian. Well, we would like to say that the coordinates Rn are given by the equilibrium position, which is just n times A, okay, plus phi, where phi is the displacement, okay? Now, how do I quantize this? First of all, I do this, okay? That's the first stage is just to draw hats on all the variables that appear here, okay, including the Hamiltonian. Once I do this, what I mean by what is P hat and R hat, they are now quantum operators. And what I know about them is that for each particle, so each particle, if we start from the original masses, the corresponding Pn and Rn obey canonical commutators, right? And the commutator of Pn and Pn plus 1, let's say, what is it? No, of Pn and n plus 1. Zero. It's zero because they are independent. It's a different degree of freedom, right? So each momentum is conjugate canonically conjugate to the coordinate of the same particle. So if I want to write it compactly, I can write it like this. That yes, exactly, right? Okay, yes, yeah, exactly, right? And by the way, if the particles were in a higher dimension, then also each component of each coordinate of each vector will also be an independent degree of freedom and obey commutators. But we are in 1D, so it's simple. So these are the commutators. If n equals n prime, we get IH bar. If n is different from n prime, I get 0. So to write it compactly, I just have a delta, Kronecker delta of n prime. Okay? Okay, very good. Sorry?
Rn plus 1 and Rn, they are supposed to be switched.
Sorry, you are right. Yeah, sorry. All right. Okay, let me correct it by doing this. Okay. Thank you. Yes, that's right. Good. Okay. Now, actually, you see that this expression is a bit confusing because if I plug in the splitting of R to equilibrium plus displacement, the equilibrium part will drop out because we saw it last week, and then actually this term is just phi n minus phi of n minus 1, right? So it's only expressed in terms of the difference between the displacement. So I want to now plug in Rn to be, again, a constant plus phi n. The constant, the equilibrium position, is a C number, okay? It commutes with everything. And therefore, this commutator is also the same as the commutator of phi. Okay? So if I plug in Na plus phi, phi is indeed an operator, but the Na commutes with P and therefore doesn't change the commutator. Okay? So these are the variables in terms of which I eventually write my field theory, right? And I know already what are the commutators, but this is all within the discrete version where I have an index in. I want now to go to the continuum limit in order to do it for the field phi of x and its conjugate momentum, which is pi of x. We saw that we can convert the continuum Lagrangian to a Hamiltonian, and in the Hamiltonian, I will have, instead of the Pn's, I will get something I call pi of x, which is the continuum limit of the momentum. Okay? So let's do the conversion and use this as a starting point. How do we do it? We saw it last time. We convert phi to to phi x, okay? By doing this rescaling, we talked about the freedom we have, and let's keep it that way. And you'll see in a minute that it's going to be very convenient. And actually, we remember in the back of our heads that the a is we're going to take the limit that a goes to 0. Okay, so this is the mapping that we do from a discrete to continuum. Now we also have the momenta in the discrete version, which we want to convert to continuum fields, and the convenient rescaling is exactly the same. I take a to the half, and I'm left with a continuum version of the momentum. I already know the commutators of phi and p. From this simple rescaling, let's get the commutators of phi, sorry, I forgot the head, of phi of x and pi of x. Okay? So, yeah.
Goes to 0 in a p?
For the moment, we keep it.
Okay.
Okay? But in a minute, we'll do something which will take it to 0. But we keep in our mind that it's small. The whole point about going to continuum limit is we want to forget about the a and take it to be infinitesimal. So let's plug in this rescaling. I plug it into here. And because I have a to the half times a to the half, I can take out from the commutator a constant a, right? Times phi of x, pi of x prime, where again the x prime is related to n prime by just multiplying by a. Okay? So this is equal to I h bar of delta of n prime, which I can, remembering that x is n times a, and x prime is n prime times the same a. Okay? So delta of n prime, formally you can write it as delta of x prime. I deliberately write it like this. It's still a Kronecker delta, but this is what I mean. Okay? Okay, so we are now almost done, because now we're going to divide the two sides of this equation by a. And we are going to get that phi of x prime commutator is, and this is where I also want to take the limit at a goes to 0. So we're going to define it as the a goes to 0 limit of a Kronecker delta x prime divided by a. Okay? Now the Kronecker delta is dimensionless. Okay? If we divide it by a, what do we get? We get something that is that first of all has units of density, right? It's 1 over length, and what is this? Exactly. This is just the definition of, sorry, I forgot the, yeah, there is a factor of IH bar. So this is nothing but IH bar times the Dirac delta function. Okay? Okay, so let me write the final result. So this is what we got so far. We see that these local fields that are canonically conjugate in the continuum limit, all that happens is that the Dirac, the Kronecker delta turns into a Dirac delta, okay? But it's still the good old conjugate momenta and coordinate that you are familiar with. Okay, very good. So, and again, I forgot to maintain the hats here, but it's becoming a bit exhausting to write a hat all the time. So from now on, let's make an agreement between us. I'm not going to write the hat, but from now on, we are in the quantum world, and these fields are quantum operators. Okay? Agreed? Okay, great. So let's go on with this and write the Hamiltonian. And now it's going to be a quantum Hamiltonian. Okay, so I'm writing it like this. And by the way, let me, in this lecture, I denote the length of the chain by capital L. We are typically interested also in the case that L goes to infinity, but let me just write it because the letter I used last week may be used for something else. So don't confuse this L with a Lagrangian. Okay, it's length of chain, okay, or the string. So it is given by the, okay, let me just write it. Like this, the Hamiltonian density. And let me write it explicitly. Or you don't like the curly brackets, so. Okay. So it's pi squared over 2m plus rho s over 2 grad phi squared. Okay? This is the Hamiltonian. We got it last time. Actually, it is nothing but a continuum version of the discrete Hamiltonian we wrote in the beginning, but we could do this directly. Okay, so we have a quantum Hamiltonian, and we have here the conjugate coordinates and momenta, but there is a problem with this Hamiltonian. It's not so convenient to work with it. And what is the problem? I don't only have here a function of phi, I have a derivative. Okay, so the potential energy is not local. Okay, and we know why, because it comes from the coupling of two adjacent particles in the original chain, right? So, so this is not something that depends only on the, it's not just a local thing. So the space description, the space basis for describing our local fields is not convenient for that reason. And if you want to go, we can go always to another basis by which we should describe our fields. and that's true for both the classical and the quantum problem, we can go to Fourier space, right? Because every time we see a derivative in Fourier space, it's going to be just a factor of k, okay? Just a constant. So I'm now going to do a Fourier decomposition. And by doing so, I'm going to switch from the operators, the quantum fields, phi of x and pi of x, to phi k and pi k. And we'll see that since these are also quantum operators that have to be consistent with this, they're going to give us some commutations. So let me first write the definition. So first I write phi of x as 1 over L to the half. This is a normalization factor. Integral from 0 to L of, sorry. This is I started to write the inverse transform. So this is sum over k of phi k e to the I k x. Okay? Now, why do I have here a sum? So I'm assuming here that it's actually a Fourier series, not a Fourier transform. Why is that? No, we'll get, you're jumping ahead, but why is it a sum and not an integral? In fact, it would be an integral in the limit where L goes to infinity, but if L is finite, okay, L is the length of the string, and these k's are actually going to define for us some wavelength, right? Because 2 pi over k is a wavelength, and if you have a finite medium in general, the legitimate solutions have to obey boundary conditions. Okay, some boundary conditions. The boundary conditions are going to give us a discrete set of k's for which it is obeyed. And now, what are the values of k specifically? Now it depends on the choice of boundary condition. Let's assume that the boundary conditions are periodic boundary conditions. Namely, actually, what we are assuming here is that our string is a loop, it's a closed loop, okay, of circumference L, and therefore, you write it like this. So this is L, and it's also 0. So the point 0 and L are the same, or in other words, periodic boundary conditions assume that phi of 0 equals phi of L, and the same is true for the momentum fields. Okay? And you already know from your many other courses in undergraduate that what are the allowed values of K then? Right, exactly. So the K is going to be 2 pi over L times some integer. Right? So these are the quantized value. Of course, if you take the limit at L goes to infinity, it becomes a continuum. Okay? This is the usual thing, but let us maintain the sum, okay, for now. Because what are the different cases? They are different. What do they describe physically, in fact? What do they describe? They describe...
Pi.
Yeah, I'm going to write...
No, it's supposed to be pi.
Ah, sorry. Yeah, sorry. Yeah. Thank you, right? Yeah, I'm going to write here the pi of x, and there is some convention that makes it a little different. Okay, so, but first I want to talk about the physical. What is the physical meaning of each of the phi of k? So phi of k no longer describes a local field, right? Because it's not a function of a point in space. It describes some mode, right? So we know that the solutions of the free string equation, wave equation, is that you're going to get some modes, which are, these are oscillation modes of the entire string. And the oscillation mode, each mode is extended over the whole string, and it looks like some vibration, okay? It's an extended thing that obeys, of course, the boundary conditions.
What?
Yeah.
So each particle has a different mode, or
No. So each mode is a collective creature made of vibration of all the particles. Okay? So you can have, if you think of a discrete chain, then one mode may be, something that looks like this. Okay, so so each of these modes is, if this is the equilibrium position of the string, then a mode is an oscillation where all the particles, or almost all of them, deviate from their position such that they create some sinusoidal disturbance. Okay?
you have different modes for.
So each node has a different wavelength. This is mode, let me call it mode 1. Okay, sorry. This is mode number 1. And mode number 2 will be, of the same string, will be something like this. So it has a much bigger wavelength. Okay, it's a different mode. And you can have, actually, for each k, you have some wavelength, and this wavelength has to be L divided by an integer. Okay? Exactly, it's a collective, exactly. So the mode fields are if you try to relate them to the original particles, they are collective objects. Okay? But fine, I mean, there's nothing sacred about local or the original particles. There's nothing sacred about them. In fact, the philosophy of particle physics or high energy physics is that all the particles, including protons and electrons and all of these may be emergent particles from some more basic who knows? Okay, you're never going to be able to prove that there is nothing underneath, right? So, yeah. So
זה מתאר תנועה קולקטיבית של כולם בתצורה מסוימת עם יחס פאזות מסוים. זה בעצם מה שמנסה להגיד. ועם הזמן אנחנו יכולים לראות איך זה מתנהג.
Sorry, let me translate to English. It's not that there's different phase. Each mode has different wavelengths and a different frequency. Okay,
כל אופציה של מודה.
right. Okay. So let me just finish writing the mapping. So if this is phi of x and this is the same, we're going to do the same Fourier decomposition for the pi's, but there is some little difference. We have here some freedom to relate the k's of the phi to the k's of the pi's, and I choose, this is, you'll see that this is just for convenience. It's convenience to choose here to put a minus sign, okay? But it's a matter of definition, okay? Yeah. In the phi, we have a positive ik, and the pi will have the negative. Now, if I write the inverse transform to get explicit expressions for the phi's, this I can erase, right? Okay, so from here I can write the inverse transform. So phi of k is going to be the integral of e to the minus I kx times phi of x, and pi of k is e to the plus I kx times pi of x. Okay? All right. Now, what do I want to do? I actually want to switch from a description in terms of pi x and phi x to phi k and pi k. So I just take this formula and plug it into, I want to know, first of all, what are the commutators, right? Because now there are some quantum operators. I want to know what are the commutators. And not surprisingly, you can see that these two are some canonical commutators. Where should we write it? I think we can, actually I don't need this anymore. Okay, so phi k commutator with pi of k prime. Okay, let's do it carefully. So I just take these two expressions and plug them in. I get a factor of 1 over L, and then there is a double integral of x and x prime. Okay, both of them are from 0 to L of e to the, now let's do it carefully. So this is going to be okay, there is an inconvenient minus sign, but never mind. Minus I kx plus I k prime of x prime times the commutator of phi of x and pi of x prime. Okay? But we know that this is a delta, right? This thing is IH bar times a delta, a Kronecker, not a Dirac delta, right? And therefore, I can easily integrate over x prime to get x prime equal x. So after integrating the delta, I'm getting the following results. First of all, there's a factor of IH bar, 1 over L, and now I get 0 to L of e to the I, k prime minus k of x, right?
Another derivative.
Yes, exactly. So what is this? Actually, if you like, in the limit that L goes to infinity, this is exactly a delta of kk prime. Yeah.
Why do you have the commutator there in the integral?
So I just, what I did is the following. I have a simple relation between phi k and phi of x, and the same for the pi. Phi of x and pi of x obey these commutators. This we already proved. Not proved, we know, right? So I just inserted them in the commutator, okay? Everything in front is just a C number, so I could take it out of the commutator. Okay. Let us not take the limit L goes, yeah?
רגע, אבל כשאת עושה את יחס הקומוטציה, את יכולה לעשות את הראשון כפול השני, ואת השני כפול הראשון. עכשיו, הראשון, כי את עושה באינטגרל בנפרד, השני את עושה אינטגרל בנפרד, ואז בגורם השני את גם עושה אינטגרל לשני הגורמים בנפרד.
Let me make it, okay. Let's write a small reminder, okay? If I have two operators, A, B, that have some non-zero commutator, if I multiply them by C numbers, first of all, I can multiply them by C numbers. Okay, B times, sorry, C2, okay. If C1 and C2 are C numbers, you agree that this will just give me C1, C2 times the commutator, right? Now I can go on with this. Now I do a summation over C1 and C2. And it's going to be a summation, nothing, just term by term. Now take the limit to it. Okay, so this is a trivial relation. What? Sure. Okay. Now if I'm looking at this, so in the limit that L goes to infinity, it actually becomes a Dirac delta for the k. But let us, if we keep it finite, this integral is going to be 0 if k, because remember k is, I already erased it, but the k's are periodic, are quantized values 2 pi over L times an integer. So it's going to be 0 unless k equals k prime. And if k equals k prime, the integral gives L divided by L, and you get 1, right? So what is the result of this calculation? Let me write it down just below. This was a mistake, but never mind. So what we get here is that phi k prime is going to be I h bar times delta of k and K prime. Okay? Yeah, okay? So you see that this is very nice because the modes, now we are not talking about coordinates and momenta of particles. They are momentum of and coordinates of some modes. Okay, so it's a bit more abstract thing. We're talking about objects that are extended, that are collective excitations of the string, not just one particle, but nevertheless, they obey canonic commutators that look very much like a single particle. Okay? Okay, so now let us plug this Fourier transform into the Hamiltonian. And apologize that I erased it, but let me write it quickly. The Hamiltonian was in real space was pi squared over 2n plus rho s over 2 grad phi square. Okay, and what is the Fourier transform of? So here, if I'm going to do a Fourier transform for each pi x, I'm going to get pi k. What is the Fourier transform of grad phi? It's IH bar times phi k, and because we have it square, if you do it carefully, I'm not going to do the algebra. Okay, let's leave it just to save time. Please do the algebra yourself. The algebra is very simple. Just take these expressions. Now we have to use this the direct Fourier decomposition. Just plug in phi x and pi x and denote the sum by k prime, and then you'll get, okay? And you'll see that after integration over the length, so what is going to happen here, just to sketch the calculation, which I'm not doing, if I plug in pi square and grad phi square, I'm going to get two sums over k and k prime, right? But then the factors of all the x dependence, x and x prime, is going to be embedded in the factors of e to the ik. And after integration over x, I'm going to once again get a delta of k prime. But if you do it carefully, it will actually give you a delta of, so let me write it here, 1 over L times e to the I k plus k prime. Okay, what is this? This is a delta of k and minus k prime. And if you do it carefully, you're going to find that the Hamiltonian has the following form. It's a single sum over k of 1 over 2m pi k pi of minus k, and okay, sorry, we write it more nicely. Sorry, I'm just repeating. Maybe change the 1 over 2m plus and k squared, phi k, phi minus k, phi k. Okay? And let me go one more step and remind you that from the parameters of this theory, we have the stiffness, rho s, and the mass of the original particles, capital N. And we saw in the wave equation that it defines a velocity, right? So there is a velocity, which is the square root of rho s over m. And if we just massage this second expression, rewrite it a little differently, we can see that okay, so it will give me the following expression for the Hamiltonian. Sum over k of this, I leave it as 1 over 2m pi minus k pi of k plus capital M omega k square of phi minus k phi of k. Okay, and this is the final result I want to leave for the expression for the Hamiltonian in terms of the modes, the mode field, phi k and pi. Okay? Now, what is this omega? So here I introduced something that has units of frequency. And what is this frequency? It is nothing but change of variables. You can easily convince yourself that omega k is in fact nothing but v, this same velocity, times k. Okay, so what is this? These frequencies, they describe frequency of the mode, and there is a very simple dispersion relation relating omega to k via a constant velocity. Okay, and the velocity is just the constant velocity that you get from the elastics. Okay? So this is now a quantum Hamiltonian. What does it remind you of? That's right. It describes. It reminds. We have to be a little more careful here. So if I'm looking, first of all, it's a sum over independent modes. That's one thing. So each mode is independent. Okay. It already simplifies the problem. So and each mode is an independent quantum operator and with the corresponding commutators and so on. And each mode reminds us of the form of the harmonic oscillator, but not quite. What is the difference here from the... So let me remind you how the Hamiltonian of a single harmonic oscillator looks. Okay, this I think we can definitely raise this now. So how does it look like? Just a single particle in 1D. It has x and p, right? The two, and where x is now going to be, don't get confused, okay? It's the coordinate, which is a quantum operator, position operator. The harmonic oscillator is p square over 2m plus half m omega square x square, where x and p are quantum operators that obey the canonical commutators. That's the single harmonic oscillator, right? Now, what is the difference between, so I want to say that each mode is a separate harmonic oscillator that has its own frequency. The frequency depends on k, okay? But what is the difference between this expression and this? Right, okay. So, wait, that's very good. You're getting to what I'm heading at. Here, the operators appear just square of the same operator. What can we say about, what do we know to say about the coordinate and momentum operator of a single harmonic oscillator? They really describe physical quantities, right? Measurable quantities, and therefore, what kind of operators they are?
Hermitian.
They are Hermitian, okay? They are Hermitian. X dagger equals x, and the same for p. However, phi k and pi k are not Hermitian. How do we see it? We know that the original coordinate and momenta of the particles were Hermitian, because they really describe coordinate and momenta. So we know that, and the same is of course true for their continuum limit. So phi x equals phi dagger, and pi x equals pi dagger. These are Hermitian operators. But what is phi of k and pi of k? They are, no, what are they mathematically? They are defined, let me write it again. So phi of k is an integral of e to the I, sorry, here it's plus I kx phi x, okay? Now, this is a Hermitian operator. What is phi k dagger?
Minus I.
Exactly, right. So when you take the dagger, when you multiply it by a complex number, you have to take I to minus I. So it's, let me write it explicitly. So it's e to the minus I kx, but phi dagger of x is phi x. So what is this? Exactly. This is exactly the definition. The right-hand side is nothing but phi of minus k. Actually, this is a formula that you want to remember if you are awakened at 2 o'clock in the morning, as we said, which is that every time we have a local operator that is Hermitian, its Fourier transform obeys that phi k of dagger, the phi k dagger is phi of minus k. And the same, of course, is true for pi. So in fact, when I'm writing this and remembering that these are non-Hermitian operators, I can rewrite it as pi k dagger pi k plus phi k dagger phi k. And now it starts reminding you, I think, of What does it, I mean, does it remind you of something?
Okay.
Okay, so they're not quite, but we still have two different operators, phi and pi, but since they're not Hermitian, we already gave up on getting a square of something plus square of something, but if you write them, you can write it as sum over a single k, and in each k, it's a quadratic form that has pi dagger pi and phi dagger phi, so it reminds very much of the expression for the harmonic oscillator with a dagger a. But since we mentioned them, let's go to the next step, which is to introduce a ladder, just like what you do for a single harmonic oscillator. And I hope all of you learned it. You know what we're talking about? I will remind.
Of course.
Okay?
And maybe you can remind.
Yes, I will remind because we're going to generalize it. And we are going to do the same thing for our problem, where now, because we don't have just one harmonic oscillator, we have many. But basically, this is nothing but a set of harmonic oscillators with different frequencies. That's what the problem is. And this is going to define our true degree of freedom, in a sense. Okay? Okay. So let's do it. I first want to remind of the harmonic oscillator, the single harmonic oscillator. So I'm going to do this. So now if I start from this Hamiltonian, you see that it's expressed in terms of P and X, and they obey canonical commutators. But it's very convenient if you just want the spectrum of the harmonic oscillator. Let's first see what you remember from undergraduate. So what is the spectrum? What is the energy states, the energy eigenvalues of a harmonic oscillator?
Omega n.
That's right. So this is how it looks. So if this is the harmonic potential, you get it's a very special case where you get an extremely simple expression for the energy spectrum. And it is an equidistant ladder, okay? In any other quantum problem, like a square well the hydrogen atom, you get some formula that the states either become more spaced or less spaced. In the harmonic oscillator, there is a single energy step. It's very, very special, okay? And the expression for the energies is En equals h bar omega times n plus half. So where n is starting from 0, 1, 2, etc. The 0, which is the ground state, gives you a finite energy, half h bar omega, which is so-called ground state energy. So it's not 0, okay? And all the others, and this is the ground state, and all the excited states, the higher energy states, are just equal spaced in energy. Okay. So now what we do for the harmonic oscillator is to define ladder operators. Let me do it here. I'm writing a definition first. A is this is the definition, right? So, what is the motivation for doing this? I see that here I have two different operators, x and p, but the form is very similar. Both terms are quadratic in x or p. So I want to change them into a single species of operators that is just a linear combination of x and p, rescaled in such a way that they will have the same units, and the linear combination of the p and x will give me some operator that will appear in the expression with its Hermitian conjugate. So the first, so what, this is this operator little a, and it's defined as okay, let me just check that I'm correct with all the factors. And notice that x and p are Hermitian operators, but because of the I here, there is a is not Hermitian. What is a dagger? Exactly. So so this is x minus I omega. And now it is easy to check. I'm not going to do it. You studied it, but I'm just reminding. If you apply the canonical commutators for x and p, you can convince yourself that the commutator and a dagger is, what is it? Remember? Just one. Okay? Actually, I have here this square root of m omega h bar, so you can easily convince yourself that this expression has dimensions of 1 over length. And that's why a and a dagger are also dimensionless. Okay? So the h bar is somehow buried in them, but in such a way that they really, they're described pure, I mean, they are dimensionless objects, and their commutators are 1, okay, of a and a dagger. Okay, so they are non-commuting objects, and in terms of them, if you rewrite the Hamiltonian, you get h bar omega a dagger a plus r. Okay? Okay, and how do I get it? I just take x and p, plug in the inverse transformation to go from x and p to a and a dagger. This is just algebra, and this is what I get. Okay? So this actually already gives us a very good hint why the spectrum, I mean, this is still a quantum operator. This is the Hamiltonian as operator, okay? Maybe I should, yeah, okay? But it's an operator. But if you know that the solution for the stationary Schrödinger equation with such Hamiltonian gives us this spectrum where actually what is n, the integer, n is the eigenvalues of the operator a dagger a. So the operator a dagger a is in fact a number operator. It's something that counts. What does it count? If we go to the spectrum, it counts levels in the ladder. Okay? So Moreover, so we can deduce from it, and actually this is how you solve the harmonic oscillator without mentioning the word Hermite polynomial, differential equation, and all this nasty stuff, okay? Because this would be the difficult way of solving the spectrum. The easy way and the elegant way of finding this spectrum is noticing that the solutions for the Schrödinger equation eigenstates, where n corresponds to the wave function that the single particle wave function that has the eigenvalue En, and En is this. The state, all these states can be generated from a single state, which is the ground state, n equals 0, by applying the ladder operators A dagger and A. So what one can show, and I'm not showing, I'm just reminding, is that if you take the ground state, I denote it like this, right? And I apply the operator A, what do I get? I get 0. So the ground state is an eigenstate of the ladder operator A with eigenvalue 0. What does it mean? How can I interpret this? The operator A is something that if I apply it on the ground state, it just kills it. It gets 0. Okay? So therefore, it is called an annihilation operator. Okay? And therefore, what will be a dagger?
Creation.
It will be a creation. That's right. This is a creation operator. And why can we, in what sense it is a creation operator? If we apply a dagger on the ground state, we get the state 1. Okay, so if I'm going back to this, the picture of the spectrum, which is a ladder of states, what are the operators A and A dagger do? A dagger takes you from one to another, okay? So A dagger is a raising operator in the sense of going up and down on the ladder of the spectrum, but it's actually creating, what does it create? It creates an energy bundle, in a sense, okay? So, and what is the A doing? A is going down in the ladder, okay? And if you apply it on the lowest state, it goes to 0. It kills the vacuum. So that's why they are called ladder operators, but by giving them these names, I'm admitting that they create and annihilate something. What is this something? It is a quanta of energy. And moreover, what is the energy of each of these quanta? It's h bar omega. What does it remind us of? A photon, right? So these particles are, I mean, I wouldn't really call them, they're not photons because they're not particles of light, but they have the same nature, if you like. They are photon-like objects. They are particles. And for any practical purpose in physics, something that behaves like something else, walks like a duck, and so on, it's a duck, okay? So it's a particle, or if you like, it's a quasi-particle. or an emergent particle, because it's not an atom, or it's made out of collective vibrations of many atoms, but it is a particle that is like a photon. In what sense it's like a photon? It carries energy. Because it's a single harmonic oscillator, there's no meaning to talk here about the wavelength or something like that. It just has energy, only one flavor of energy. It's like a monochromatic light, if you like. And going from one state, each time we apply a dagger, actually let me just rewrite the general expression for the states n. You see that to get the state 1, I have to apply a dagger once on the vacuum, on the ground state. If I apply a dagger twice, I get the state 2, but with some normalization factor, and the correct normalization, exactly, you have to divide it by square root of n factorial of a dagger to the n applied on the ground state. Okay? So these are all the states of the harmonic oscillator, and to calculate anything to do with a quant of the harmonic oscillator, you don't need more than this. You can calculate a matrix element of any physical operator, just with A's and A daggers, and using their commutators and algebra. Okay? So what is the meaning, or what is the origin of the n factorial? I mean, how can we of course the origin is mathematics, and because we want the wave functions to be normalized, but it has a physical meaning, right? Because what are these n particles? They're all identical, right? They're identical particles. And what kind of statistics do they obey? They are bosons, right? Not fermions, but bosons. Why we say that they're bosons? Because I can have arbitrary number of them. Okay? Right. So there's actually okay. So if I want to do a mapping between the single particle quantum problem of a harmonic oscillator to an equivalent description in terms of these new particles. Okay? So in the let me draw it a little more clearly. So we have two ways of looking on the same problem. One is in the single particle language, we have a harmonic potential. Okay, this is the coordinate x, and we have these energy levels. Let me plot them. This is E0, and this is E1. And let me use another color, just I hope it can be seen. This is E2, etc., etc. I have an infinite ladder. And the difference between them, the difference in the energy between one to another is always the same. It's the one, that's a single quanta of energy, h bar omega. Okay, and that's why we can do it for the harmonic oscillator. We cannot play this game if the spectrum is not equal spaced. It's very important to remember. So when I'm saying that the harmonic oscillator is at the state 2, what does it mean? It means that the particle, this is a single particle, right? the particle lives in E2, okay? And it has a wave function with 2 nodes and blah, blah, blah. It doesn't matter. We also know how the wave functions look like, but we're not interested. So, but in terms of energy, having the harmonic oscillator at E2 corresponds to application of a dagger twice, okay? So it's completely equivalent to the following problem, where we have a vacuum level, and here I don't call it, this is in the single particle language, it's called a ground state. In the emergent particle picture, I call it a vacuum. Okay, so if the harmonic oscillator is at the ground state, there are no excitations, okay? There are no quasi-particles, it's empty. Therefore, it's a vacuum. Now, above this vacuum, there is a single level of energy h bar omega. There's only a single state, If I'm exciting the harmonic oscillator to E1, it's equivalent to, okay, so this is equivalent to, if I have this situation, it's equivalent to putting 1 particle in the level, in the energy state h bar omega. If I have 2, okay, so I'm not drawing it very clearly. So being excited to a state 2 is equivalent to occupying this energy state, this single energy state, by 2 particles, 2 identical particles, and so on. Yes, the harmonic oscillator at level 17 is equivalent to putting 17 photon-like particles in the single level, okay? So in the many particle, it's a many particle picture of the same problem, where the particles here are the number of energy quanta h bar omega that we occupy. And because we can put as many particles as we want in the same state, the same quantum state, they are bosons and not fermions. Okay? And we can call them photon-like, or if they're describing vibration modes, we can call them phonons. Okay, which is what these guys are going to be. Now, is that clear? So, this all I think you should have learned in undergraduate, but then I have to remind it, because we are just generalize it to many such things. So, so this description is very nice, because we see here that the collective object, the particle, is not a good, or the coordinate and momenta are not a good degree of freedom, because it's not a free particle. It's not a free particle, right? It's a particle in some complicated potential. These emergent particles are just free particles. They're really like photons, okay? And these commutators are encoding the fact that they're bosons. We'll see later why. We will generalize it. But, and they can be, and that's important, they can be created and annihilated. By creation, I mean that if I apply some creation operator on the vacuum, I get the particles, but I can eliminate particles by applying the annihilation. Okay? And this describes a situation where particles can be created. The number of particles in general is not fixed. Okay? I can even talk about coherent superposition of of a state with n photons and n plus 1. And it will not have a well-defined particle number in terms of these emergent particles. Okay? But these are the true degrees of freedom of the problem, because in terms of them, the Hamiltonian has a very simple form. It just counts them. Okay? And that now finally, going back to this normalization factor n factorial, where does it come from? Because if we put in if we want a normalized state, and it's made out of n particles placed on the same, in the same box, if you like, in the same quantum state, and they are identical particles, the normalization is applied by dividing by the number of permutations, right? Because if we put n particles in the same box and they're all identical, there are n factorial configurations that are equivalent, okay? So that's where the n factorial comes from, okay? Okay, so I guess we'll have to stop here, and but just to give you a hint what we'll do next. So we are going, personally, let me just take one, okay, let's do it next time. But I'm going to give you a hint on when we do exactly the same thing for the Hamiltonian written in terms of this pi k and phi k, which are now replacing the p of x of the original. And what we are going to do is to define new ladder operators, ak and ak dagger. They come with an index k, because for each mode, it's a different particle, a different flavor, a different frequency, okay? And a different wavelength. And these particles that are called phonons, because they do describe vibration of a lattice, okay? And they are going to be combinations of phi and pi, but because phi k and pi k themselves are not Hermitian, we have to be a little careful with the k and minus k. Let me do it next week, okay? But otherwise, it's all the same, and we're going to get a simple Hamiltonian that is just a sum over k of something like this. That's all. Okay? All right, so the next session is going to be given by Sar. It's the tutorial today. So I'll see you next week, unless you have questions. We have some time.
In class, I'm not sure exactly how much Efrat went into details, but you talked about the classical field theory and specific application on the electromagnetic field, right? Something like that. So today, we're gonna start with a little recap of the electric field. We're gonna introduce the concept of four vectors and this type of shortened writing that's used in the electric field, in a field theory. And then we're gonna find the Lagrangian and show that it's the correct one. If we have time, which I don't think that we'll have time for this, we'll also go into detail on northern theorem. Did Efrat mention it? Something? Oh, okay. So let's hope we'll have time. At worst, you'll see it in your homework, with of course, with some guidance. So,
It's your Gmail.
oh yeah. All right. This is my personal email and my phone number. Don't spam me, but you can ask me any questions and I'll answer. It might take me a little time, but I try to answer every question. My name is Sarah Levin, if you didn't get the hint from the mail. So let's start. When we talk about the electromagnetic field, we talk about two specific fields. The electric field, which has 3 degrees of freedom, is a field with Ex, Ey, Z, and then we can also talk about the magnetic field, which is the second component of the electromagnetic field. Bx, dy, bz. Right? In addition, we know that we also have the density, rho, the charge density, which is 1 degrees of freedom, and then we also have the current, small j or big J, depending on how you look at it. Of course, we all remember from electromechanics. You know, first year, this is first year of first degree, the Maxwell equation that connect all of our degrees of freedom. Right. These are the Maxwell equation, where the first two are the homogeneous one, and the second one are called the inhomogeneous one.
Classical field theory זה הכותרת של הכל.
It's the everything. Oh, also another few little details about me. I have what you call dysgraphia, which is a problem in writing. So if I have some sort of misspelling or stuff like that, don't be ashamed to correct me. And if something is not clear, just say it and I'll write it again.
רק ה-EY שם, אם כבר תמצא נאי, בהגדרה של השדה שלנו.
Well.
כשאמרת בשדה E, נכון, E זה EY.
זה...
Right. Last thing that I want to do before we go into the actual subject is that we can minimize those 6 degrees of freedom into just 4 by using the potential vector, the electric potential phi, and the vector potential A. I might write 1, 2, 3 or X, Y, Z, but it's the same. Just if we write it. Can, using these two potential terms, recreate our electric field as and our magnetic field curl of vector potential. All right. Those two equations, let's just show them for a second. Let's show for a second that they match the two homogeneous Maxwell equations. Let's start with the electric field. Try to match the top one. So we'll take the curl of the electric field. Alright? And it does a curl. Now a curl of a gradient is by definition 0. So this term goes, and we're left with dou x e equal to curl of a derivative of t. I can switch the derivative in the curl and get dou t of curl A, which will be just using the second equation, will be dot equals beta of B, sorry. And you'll see that it's exactly first Maxwell equation. If we'll take B and multiply it by divergence, we'll know that divergence of curl, that will be by definition 0, exactly like here. So we got back to the Maxwell equations. This was just to show the validity of this presentation. It's different writing. We reduced our field from having 6 degrees of freedom down to 4, which will be useful for our next part. Now, find and define 4 vectors. All right. Usually when we talk about collision in space-time, we define 2 different one vector element, x, y, z, and time. When we talk about field theory or relativity, if any of you will touch on the subject, we define a 4 vector, which we'll call x mu equal to t minus r vector. Of course, this is just t6 plus 1. All right.
What under the x index?
Mu. Some sort of general index to the column. This will be called the covariant vector, and we can also define the contravariant vector, which will be x with an upper index, x upper mu, will be equal to t r vector. So far, so simple. Now, how do we move from one another? We can clearly see. Yeah, we'll just multiply it by a matrix. This matrix, you can see that we want to change the sign of the three last letters without changing the order or combining the order. So we'll just define a matrix called G equal to 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. You're welcome to check me that multiplying them will get our expected result. But also, if you want to write it in our convention mean with our indexes, we'll call it G mu u. G mu u. 2 indexes to symbolize a matrix. So to create an upper index mu u.
No.
We multiply our G mu u with x u.
Maybe you can change the marker.
I can. Oh, sure. Let's give me a letter.
Huh?
Give me a letter.
No, change the marker.
Oh. Okay. Yeah, I have another one. Notice here that notice here that the index in the bottom here of the X is different from the index on top. Basically, we say for each row in this matrix, mu, each row in this matrix we multiply it with the X and will correspond with the position mu in our 4 vectors, right? So mu, let's say for example, mu x0 will be equal to g00 x0 plus g01 x1 plus I'm going into fine detail with this type of writing because it can get a bit complicated. So can I delete this? Can I erase this? Okay. So now that we define how 4 vectors work, we'll define the 4 vectors that we see, that will describe all the elements that we use here, that mean the potential and the density and the current. So we'll start with the can you see this? Should I replace it again?
Replace.
This is the last one, so you better hope it's good. Alright.
Oh, now
It's very strong. G. We also define our potential vector equal to phi. And lastly, we want to define our derivative vector. We will define. Notice that in the derivative, it's a special case where we don't have a minus on our vectorial term or space element. This? I'm just defining useful vectors for the future. Look here. Basically, we distilled all of our equation to be dependent only on the potential and the currents and charge density. So I took all these terms and put them here. So we'll define a new operator, a new matrix, F mu u equals to mu right. This matrix you can see the map. You can see. Okay, let's just take a moment here, because this can complicate some people. I saw people get complicated by this. Notice that we have multiplication of 2 vectors. So you can say to yourself, it could be a number or it could be a matrix. So the way I look at it is I'm trying to look at the entire. If we have a complex equation, try to look at the most clear element in the equation and see what is it. Since we know f is 2 free indexes, it must be a matrix. So the right side will obviously also have to be a matrix. Here it's pretty simple to say because we already see that the derivative and the potential don't have the same indexes, so there will be 16 terms and not 4, like a vector or not 1. All right. F
שפה אנחנו בעצם מגדירים כל איבר לחוד במטריצה באמצעות
Yeah.
זה.
This will be every term independently, but let me just give you a little spoiler. In the future, we'll talk about the Lagrangian, and we'll see that we have a term that goes like u f u, and this. Again, this might seem like a multiplication of two matrices, so it will give us a third matrix, but we know that the Lagrangian is a scalar, so this also have to be a scalar. So instead of a matrix, there's like a hidden sum here. We don't write. My prettiest matrix, but I think you can understand it. All right. Do you want me to like, let's say, do a column, for example, just to show it how we get to this? No. All right. Yeah, I'm gonna do the first column. All right. So. First column will be f mu 0. Let's write it. Let's write it here. F mu 0. Mu times the dot t. Dot t. And a mu. So let's go one by one. And where do I have space? Can I erase this?
Yes.
Okay. So let's start one by one. F00 equal to dot t rho phi plus minus dot t of phi 0 F10 equal dot t ax minus no. Dot x. And I erased Maxwell equation, but this let me just remind us that the vector I can clearly see that Ex will be equal to minus this one, this equation. It's a minus here somewhere. Here. Equal to minus Ex. And I'll stop here. I'll let you finish by yourself if you want. Yeah. Okay. So we can also define this the contravariant of the f function to be pretty sure I put finding this matrix in your homework, so I'm just going to go over the two basic ways. The first way, you can just calculate it directly from the definition, equal to u minus you can calculate it directly from here, or we can do what we did before and try to where did I do it? Here. And try to move the indexes up. But here, because we have two indices, you get f u equal to g alpha g. Oh, right. I knew I forgot to check something before I came into the first. I'm going to send an email. But if it's anything like last year, it's 90%, 80% test and 20% homework, I'm pretty sure. And I do check homework, so I do it.
אבל מינוס x רשום שם בשורה השנייה בקורנצי?
Yeah, there's a minus here.
למה יש שם מינוס נגזרת אפקטיבית וגם מינוס נגזרת x?
Where's the definition?
איך אמרת רק שמעלים את האינדקס למעלה פה ב-FUP? אתה מעלה, כאילו זו הגדרה ישירה של האינדקסים או משהו?
Yeah.
איך אתה מבצע את העלאה מ-FU למטה P?
From this.
איך אתה מבצע את העלאה משם לשם?
You know what? I'm going to leave it to your homework, but I'm going to give you a hint. Take this equation that I've given you and try to put it here. You'll see that 1g will up the mu, 1g will up the v, so I just solved it. So
בעצם שתי הדרכים זה פשוט שני השורות שרשמת פה האחרונות, נכון?
yeah, but this is calculating by hand, this is calculating in the smart. Alrighty. So what can we do with this F matrix? First thing we can do is get the homogeneous Maxwell equation by simply taking the derivative u f mu g. Let's just check this claim with an example of mu equals 0. So dou t f 0u equals ju. Sorry. Okay, let's just stop here for a second, and I got confused, so I'll explain. You see that this equation seems like it's defined for mu and u separately, but we actually this is a equation for each u here. So for each u, we run over the different mu's and get this vector, j vector. So start with u equals 0. We see from this definition here that we will have the x plus the y plus the z equal to the divergence equal to rho, which is again, if you remember, the first inhomogeneous Maxwell equation. Right, so So now we're starting with a real disk. Alright, now we're really going into classical field theory. Let's see where I can get some space.
Can I check? Take
Alright. So field theory starts by, not surprisingly, taking a bunch of fields. Okay, we have some numbers of some fields, and we also have all the four vector derivative, and we know that we can express Lagrangian density using our field and their derivatives. And then from here you can get the Lagrangian if you want. And from the Lagrangian you can go into the action. And furthermore, field theory, we can see that we have an integral on our full space-time dimension. So we can just write S equals d for x.
explain what you mean with steps?
Oh, this is just a normal Lorentz-Lagrange theory.
Okay.
Just apply it to some fields.
Ah, okay.
And now for the step that people actually care about, the Lorentz-Lagrange equations. To solve, to find the minimum of the action, we know that we can take do L and do I minus the Euler-Lagrange equation. Right? Note that we'll have n different equations, which each equation will have one and then another 4 terms. Alright. Lastly, just to wrap up the Euler-Lagrange theory, we can also define the canonical momentum, pi of I, equal to no. Again, 0 here, it's actually time. And finally, oh, this is fat. You can find the Hamiltonian density equal to sum over I. Minus delta H. Now after we did this quick recap, we can go back to classical field theory and try to use this to examine our electric field, electromagnetic field. So, we'll start by guessing the Lagrangian density. And I, as an all-powerful tutor, will randomly, obviously, totally random, take a guess. What is the
Hamiltonian density of Phi multiplied in the sum?
Okay, I might. Ah, yeah. Let me just. So again, this is a total guess off the top of my head, and definitely not in the notes of Yudkin. C2 mu. And again, as I said before, all of this one are indices. So there's two hidden sums here and one hidden sum here. Right. So this is my guess. My educated guess, and I want to see if it's actually correct. So what can we do? What can we do? We can try to find the Maxwell equation using this Lagrangian and this equation of motion. Let's try it. All right. So because I already use the mu and u, I'm not going to use mu here, I'm going to change it to a different index. Let's write it like so. For that, our fields, phi I equal to a u in this case. Our field is just a potential field. All right, so now we can see. A rho minus sigma rho sigma.
Sigma.
Notice that I didn't use mu u again because we already have them in our Lagrangian definition, and I don't want any mix-ups. All right. Let's do it term by term. All right, the first term. Let's remind ourselves F mu u.
יש פה סיסמת איינשטיין בתוך הביטוי הזה? האחרון של אוילר לגרנג'.
This one?
כן.
Yeah, there's a you take each row, and over here there's a hidden sum on sigma.
אוקיי, רגע, אבל אם יש לך באמת סיסמת איינשטיין, אתה צריך שיהיה אינדקס אחד למעלה ואחד למטה לצורך אפשר.
I might have made a mistake. No. You're right. Usually you're right, but here it's a little bit more complicated because we have the derivative on the bottom.
אוקיי, שנייה, אז מה שאתה בעצם אומר פה זה שיש לנו סיגמת איינשטיין לפי סיגמה עבור רון נתון.
Yeah, the sigma for given row.
אוקיי, אז כאילו אני עושה את זה בכל הרולים, זה סכום הקוסט.
Yep. So again, let's remind ourselves that f mu u is equal to mu minus mu a mu. So clearly, this term will not be a part of our when we derive by the function itself. So we can just take the second term. So it will be a row of C2 a mu j mu should be equal to C2 delta row mu j mu to just C2 j row. Now the second part of our order of approach. We want to find this right here. But notice that we want to find the derivative based on our covariance vector, not contravariance vector. That means our indexes are lower. And we have here an f with an upper index, which I wrote here. And we don't know what's this derivative. Derivative of the up vector times by down vector. So what we can do is, let's open it. Let's open the f mu u and see what we can do about this. Plus u So now again we need to remember that this is an index, and there's a hidden sum here, sum on mu and sum on u. So let me just write it here just to make something clear. So we have a different sum. U, U, 3. Right? So you would agree with me that it will be exactly the same if I'll switch them. So that means that it will be exactly the same if I'll switch the indexes, the letter of the index. This is the top U. Right? You agree that I can call this U just it's just a name. I can call it mu, and this mu I can call it U. I say this has a double sum. Just like I can switch the sums, I argue that I can switch the index. The index. Exactly. So I'll switch here the index for mu u, switch them here, and again do the exact same thing with this one.
זה גם נכון משום שהם רצים על אותו טווח, נכון? סתם כאילו היה אפשר להחליט. גם זה נכון משום שהם בעצם רצים על אותו טווח מ-0 עד 3, נכון?
Yeah. Each one of those has 16 different elements, and I just count them in different order. I'll switch. So finally,
Why you erase the sum?
oh, we don't write the sum in this convention of writing. I just put it here to explain why I can do a little trick and switch them and switch the names.
But when you write the sum, it was from 0 to
0
which
to 3.
number? What?
0 to 3. In 4-vector convention, we start at 0 and 3 like a
okay.
computer.
Okay, yeah, I know.
The first term is supposed to be derivative instead of a mu a.
Thank you. Alright, so we vastly simplified our equation, and now we can do the final little change, so we can find the derivative of it. So we can define u equals g u alpha, let's say, for example, so alpha a mu will be equal to g u alpha a alpha, and then the same thing with our second index, g u beta, then u g beta okay, just a small little detail. The u and u, dom u and u, and also the other cross terms are in the same sum part, so we can just use the same index on the g. We have to take two different g's to remove them, two different indices. All right. Next, g is just a diagonal matrix, so I can move it. I can move it back from linear mathematics. All right, so I can take the g all the way back to the equation. Finally, we get u equals 2g. Oof. And this one, we know how to take the derivative of it. All right. Anyone have any question before I continue?
מה אמרת בנוגע ל-GU הזה כאן בהקשר שאמרת לפצר לו את מה שאמרת ש-GU, שלא, ש-GU אלפא זה אלפא, כשאמרת שיכול להיות
Why do you need an alpha and a beta?
כן.
Yeah, because let's take for example a mu and the do u. Both of them are in the same. They are here. Both of them are in the same sum. There's a double sum here. So we can't have them both running on the same index after we reduce them.
זה בעצם אומר ששניהם באותו סכום בעצם, אז אתה לא רוצה
If I'll, let's say, write both of them as beta, we'll get like a sum of a 4.
Yeah,
Four sum numbers instead of 16.
כן, פשוט לקבל פחות.
This is at least how I think of it. You can also think of it as a matrix, like how we do matrix multiplication, and there will be multiple. It's the same. Right. So, again, this derivative, right, equals 2c1 Right. Now we'll take the derivative by parts, with the reminder that equal to tau. Right. So again, wow, this is taking too much space. So overall we get, if I can write again. Right? Now I can take all the g's back in and raise our index, or our index for the indexes, and C1. Notice that the indexes changed based on what we have in the G, not on based on our original G, what we have now. Right? We get for C1 sigma rho. And now delete, I'll erase this one. Last year I taught in the room 301 with the moving ball. I hated it. This is better. Right, so putting everything that we found back into our Lagrange equation, C2 J rho times 4 C1 dou rho F rho 0. Or if you remember earlier in class, we found a very similar equation. We found that the equation that can describe Maxwell equation, the inhomogeneous Maxwell equation, will be d mu f mu u was j u. So we know that C2 is is equal to 4C1. Alright? Alright. That's the time. Then we wouldn't make it to Northern theorem. It's very, very cool. So if anyone wants to talk about it after class, I'm here. I'll stay here. It's like my fourth favorite subject in this class, maybe. So this was one half of the proof, complete solution. Let's look at the energy for a second. Specifically, let's say that J nu is equal to 0. We just take our field in absolute vacuum. So vacuum, no current. And we know that in this case, where there's no charge and no current, we know that the energy, the electromagnetic field, equal to 1/2 the R integrated over space square plus t square. All right. If we have no charge or current, or Lagrangian equal to C1 F mu u F mu and canonical momentum equal to the derivative of this Lagrangian relation to 0 to the time domain. We already found this. This is 4C1 F0 0.
זאת אומרת, זה שניים שווה 4C1, אתה לקחת פשוט כדי שזה יעבוד.
Yeah, so we'll get back the questions we saw earlier, describe them at
ואז אמרת, גם אני רוצה לפתח את זה עבורי, לראות שבאמת מקבל את מעשו דברים.
No, I want to find, this is our goal, and using this goal we also find, let's say C1, the value of C1.
אבל C2 שווה 4C1 אז זה כדי להתאים את הנוסחה לפני. איזה נוסחה בדיוק רצית להתאים?
We saw like this equation.
זה כדי לקבל את התחתונה מפתח. ואז ה-JU שווה 0, למה אין אנחנו?
Well, this is like next step. Next step, I want to find the energy in vacuum with no currents and no charge. And this is like from electromagnetic.
אבל זה שאין לך זרם של חלקיקים לא אומר שיש לך ואקום. יכול להיות שסתם שחלקיקים עומדים. אין זרם או שמקזזים זה.
If they don't have a charge, it's practically vacuum for me. I don't care.
אוקיי, והם פשוט נודדים במקום ומקזזים אחד לשני מבחינת זרם. עכשיו זרם, כאילו זה לא ואקום, זה עדיין שדברים. זה כאילו, אני יודע שוואקום זה לא ריק מוחלט.
You're going to be problematic this course, huh?
מה אמרת?
You're going to be problematic. It's fine.
אני באמת שואל...
No, it's a good question. If your absolute charge is effectively 0 and your current is 0, it's the same. Even if you have something in there, it's the same as just saying we're in a vacuum. As long as the particle, charge, current, whatever, doesn't affect our field, it might as well not be there.
אוקיי. לא, פשוט, איך אנחנו נראה נגיד אם הוא משפיע על הספר לצורך?
Oh, you can try to run this equation, all of this equation again, try to find, you can run all this equation again with the charge. I'm just doing it without. It's like when you have two equations and when you have like a differential equation and you have a starting condition. This is my starting condition.
וגם שיש לי שניים שווה 4C1, אז זה התחלה נוסף שלה בדי?
C2 equals 4C1. It's the relation just between them. It's not a condition that I superimpose.
זה פשוט חובה שזה היה מתקיים, קיבלת פשוט זה.
Yeah.
אוקיי.
Alright, so okay. So from here, unit density will be by mu minus 100. What's the time? Let's see if I have time to write it all out. I'm gonna write something that is not mathematical, but it's very nice just to show it. To save time, I won't write this entire matrix, but we defined it earlier, so I believe you can finish this matrix yourself. But the result of this, if you multiply them, C1 minus E squared plus B squared. So אני יכול פה? כן. So let's just open up for a second. Second term. Oh, yeah, I said it's like unconventional. I just, to make this double sum seem easier, I kind of show the two matrices. It's just this double sum, but I put the matrix for visually. Oh, this is like a sum. Again, but it's supposed to be a scalar at the end, so I didn't want to just leave two matrices, but I did want to write the matrix because it's a visual aid, in my opinion, so it's like it's been a rock and a hard place. This is just, think of it as a different way to write a double sum, which we're showing all the explicit terms. Almost. There's the first row with the first column, second row with the second column, and so on, by just following the indexes. There isn't a nice way to write it. I don't think so. Yeah, I said this is not mathematically correct. This is just a visual aid, but you can check that this double sum, which defines. This is a lie, everyone. This is a lie. Don't trust me. And plus 4C1. second. This term, the derivative of 0 of our scalar, derivative in time of our scalar field, because we're in a vacuum, would be by definition 0. So we just left with the normal vector term. H, finally H, force 1, vector. Notice that I took a minus outside. Right. Now I'm going to add some terms. I'm going to say what they are as I write them. Just to see one outside. Two. I'm going to add and subtract this term. Zero minus now we know that E vector, the electric field, and then this pen is on its last legs. If you remember, this is just by the definition of the potential from the start of the lesson, right? So we can combine these two terms together and get H. Right? Okay. Now, if we consider for a second a reverse derivative by parts, which basically I want to this time we went a full circle.
I don't know.
Yeah, it's understandable. But you can still read this, right? I don't need to write it again.
Yes, but I think
No.
after a minute it will not be long.
Yeah. All right, so few things. First of all, for Maxwell equation, this term, the divergence of the electric field in a vacuum will be 0, Maxwell equation. So this term go bye-bye. And this one will be 0. We'll be left with the Hamiltonian density. Oh, this is a good one. Just to see 1, 2, divergence, 0 plus square plus b squared. So now the energy will just be an integral over it. Okay, and the next thing I won't be able to prove right now, but I'll just say it in words. When we take a normal integral, we know that it's up to some constant. We can vary it by, let's say, if we take an integral of x squared, it will be x cubed divided by 3 plus some constant, right? But in field theory, the same thing apply, only that a spatial integral is correct up to a surface term. For example, if you sum over a full sphere, it's correct up to an arbitrary surface of the sphere. And we see here that we have a volume integral times the derivative, so this is effectively a surface integral. So it's like the constant of our normal integrals. So we can take it to 0. Yeah. No, I can do the order of operation like so, combine taking the. Yeah.
ואם נגיד אתה עושה משפט הדיברגנס, מה זה אומר? כאילו, בסדר, משפט הדיברגנס, ואז מה קורה?
This will be effectively a surface law. I mean, again, in field theory, there's a few ways to prove on this specific one, but I don't have time for that. All in writing. So it's basically like a sentence. So we'll get that total energy will be equal to 2 C1 d3r e squared plus 3 squared. C. Here that C1 must be minus 1 divided by 4. C2 equals 2 minus 1. Roll. Look so wondrously, I guess the right Lagrangian. So just to sum everything up, I took took a guess, which of course is not really a guess. And then I use the Euler-Lagrange theorem to show that it complies with the Maxwell equation and find the relation between the two constants in our Lagrangian. Then I took the energy, proved that it reached the same energy equation, and found the two constants. That's about it.
זאת אומרת, השתמשת באוייר-לגרנג' כדי להוכיח שמשיבות התנועה יוצאות אלו ומזה הגעת לטיפול.
Yeah, I found the equation of motion, showed that the equation of motion of the Lagrange equation, which the author expected, and then I got to the constant using the energy equation that again we know from electromechanics. That's basically the end of it. Unfortunately, I won't even try to fit the Noether theorem in like 10 minutes. It's like at least half an hour or an hour. But we can talk about it a little bit.
יש משמעות ל-C1 ו-C2? מאיפה הם הגיעו?
Okay. It's kind of complicated to talk about what C1 and C2 means because the one thing that I didn't really go through is we're missing a lot of constants here. Epsilon 0, speed of time. In this course, generally in this course, we'll take them as equal to 1, the number 1. Not like 1 meter per square, just 1. So the constant here they have sort of a vague, not real. I mean, you'll have to put in the constant that we removed, like the epsilon 0 and all of the other stuff to find.
אלו האינטגרציה שנוצרו באיזשהו מקום מסוים.
Yeah. Saying exactly why we picked it like that, I'm not sure to say. Some general guess. What of the generalities? Alright, so there will be no theorem in your homework. If I remember correctly, the homework that I wrote last year, I added a question about Noether theorem, and now I'll remove it, so there will be just one. With like a step-by-step guide. The base of it is like it's a very interesting mechanic in physics that shows that symmetry, any form of symmetry, dictate some form of a constant variable. Like, for example, you'll see in the tutorial that the symmetry in time shows us that we have a conservation of energy. This law, Noether law, has some weird implication when we don't have symmetry. So we might ask ourselves, when do we not have time symmetry? The Big Bang. In the start of the universe, I don't know if any of you like saw a podcast or something like that, but there was a spontaneous creation of matter and antimatter, basically positive energy and negative energy. And it wasn't totally zero because there was no symmetry in time. So there could be some skew to the positive energy and negative energy of masses. That's the short gist of Noether theorem. There's like a big proof of it. I'll suggest you read it because again we don't have time in this 1 hour and a half lesson, and come to it with questions. It's a bit more complicated than what it could be, unfortunately.
אתה בעצם אומר שבעקבות הנוטציה כזאת היה בעצם מצב שלא בהכרח היה שווה האנרגיה התלותית ושלילית.
Yeah, if I remember correctly, it's for every million antimatter particle, there were 1,000,001 positive.
זאת אומרת, אבל זה קשור לאנרגיה שלילית.
You can look at antimatter again. This is not really my field, so there is a possibility that some physicists will come and hit me. But you can equate real matter as positive energy and antimatter as negative energy. You will. I don't know if we can talk about it. I don't think we have fine time.
רגע, זה חיוני כרגע להמשך הדיסקשן שלנו בנושא הזה?
This is.
לא, חוק נטר אני מתכוון. לא חוקרים את מה שאמרת על המפצה גדול.
You can see it in Noether's law. It basically, Noether's law shows that because you have time symmetry, you have for conservation of energy in a closed system. So if you don't have time symmetry, you don't have conservation. It's sort of if and only if. Yeah, I don't think we'll have time to do it in the next class because we really have to go to circuit quantization and solve the real mass of the course. But I find this subject, the novel theorem subject, very interesting, so it will still be like uploaded and in your homework, like a very simple question. The tutorials, I think, are already up, all of them. Yeah, I upload two different files. One, it's the Yudkin notebook. If you saw it, I'll upload it. I got it. And the second one, I also upload my personal notes. They're a bit harder to read. Again, I have problem with handwriting. But they usually have a bit more substance in them, like my personal notes. Yeah. Okay. My notes are basically Yudkin notes plus extra, a little extra.
Yudkin, its name.
Yudkin.
Yudkin.
Yeah. It was the previous. Yeah, generally yes, but almost the same. Yeah, I'll upload both of them. One of them is just it's in handwriting. I didn't have time, and I don't know if I'll have time this year to upload them into onto the file. So that's about it. Any other questions?
Next week, is there a tutorial or a lecture?
What?
Next week, do we have
a lecture? You have a tutorial once every 2 weeks, and it come with homeworks. Homework. Again, the homework is 2 weeks. It should be like 2 days work. It's usually not that long. The homework.
So אחרי כל תרגול יש לנו שיעורי בית.
Yeah, I will upload like in the same day or the next day. It's probably be tomorrow morning I'll upload because I didn't really wrote them.
התרגול, והחומר של נטר, זה אנחנו קוראים את זה מהתרגול שלך, נכון? מהתרגול שאתה כתוב.
From Yudkin's. There's also, it will be in both. You can just choose what to read.
אותו דבר מה שאתה רשת על מה שיוצא.
Again, my notes just like an expansion on Yudkin. For example, we have like a different way to think of physics, so I like to have a very like intuitive, to try to show like an intuitive understanding of what the system does and how you see it in the math. So sometimes there will be like more math in my mind, or very rarely I found a mistake in Yudkin notes. It's very, very rare.
אתה מתבסס על השמות שלך בעיקר?
This class was directly from Yudkin, but like I don't know, when we go to second quantization, we'll probably focus more on mine. Because second, this is not something that I do in my everyday work. Second quantization is what I do in my work. Honestly, Yudkin write does it better. It has. I have much less like verbal substance in my notes. So you can give at least in this subject, you can give a lot more explanation. I have another thing to say, and I forgot what I wanted to say.
So it's 20 the homeworks, 80 is the...
Again, don't take me on it, because this was with the...
Who knows? Efrat now too.
Last year it was Richard that taught this class, and now it's Efrat. And I asked her, but I forgot to write it. I asked her when I met her. It's very...
כמה זמן יש לקולגה שיש שיעור בבית?
2 weeks. Should be enough. Oh, I remember. I write notes in the homework. I try to write notes everywhere, any place that I found like a mistake or something. So if there was a question that you didn't really, that was hard for you, just check the notes on your homework. It will probably be some help.
אתה גם מעט מה אחרי, אז בעצם מה שלך נוטס על שיעורי הבית, זה מה שאתה בעצם, נכון?
No, when I say I put notes on my homework, it's when I check the homework. check the homework and I add a little like this was wrong, try turning this or stuff like that.
לא היו פחדים או משהו כזה.
No, I took this class with the Fratern. We didn't have one unless some in the middle of the year would decide to do something drastic. Then anything else? Have a great week.
You can ask. I will.
I will ask.
Okay, so you want to wait after I'm done and then you want to ask? Or
No, I will ask because it's not related to this. So when is there going to homework on this?
Yeah.
Because I'm not yet in the system. So
I'll send